Chapter 6 test. So some of these I'm just going to describe and they're not written out. So here we have a solid going to a gas. So what will happen to the temperature? Well, energy is being absorbed by the molecules that went from solid to gas. So the overall temperature in the system is being spread out among more gas molecules, which means that the average energy per molecule is going down. And temperature is the average kinetic energy, which is the kind of energy we're talking about right now. And so the average kinetic energy across the board has gone down. So the temperature is going to go down a little bit. Presumably, you have to put heat into this. I mean, the colder it gets, the less this is going to happen, the more that stuff is going to freeze, right? So the delta H is going to be endothermic. You have to put heat into this process. So that's a positive. However, very clearly, the delta S is a negative because we're going from solid to gas. And if this happens spontaneously, if it's a thermodynamically favored reaction going from solid to gas, then the total Gibbs free energy sign is a negative. Here we have a certain amount being burned, and we want the enthalpy of the reaction. So we want the standard delta H, the delta H standard. And that's measured in kilojoules per moles of reaction, and that's very key. We need kilojoules, and then we need moles of reaction. Now, the thing is, we don't know moles of reaction. What we can figure out from this is moles of chemical. Also, you're going to need the balanced reaction. Because we're using the heat capacity of the calorimeter, everything is taken into account. We know this calorimeter, we know this exact one. We've measured on it many times. We've determined its heat capacity. We don't need the mass of the chemical. We know that if you push this container up 1 degree Celsius, it took 600 joules. So then 2 degrees up is 1200 joules. So it took 1200 joules to do this, and you used 1/10 of a mole. And here's the last tricky thing. If you use 2 moles, you get 1 reaction. Or to put it opposite, because we're going to rate this per mole of reaction, if you run 1 mole of reaction, you use 2 moles. Now, one more time, for every 1 mole of reaction you run, you get to use 2 moles of this, so you get double this number. This is per moles of chemical methanol used. So you're going to get double that number, and you get this many joules per moles of reaction. For 3, we want the delta H combustion, or essentially the delta H standard. So we're given the formation values for these chemicals, but you're going to need the balanced reaction. So we know it's being burned with oxygen because that's what we do. That's what combustion means. So I balance it out. And the other little trick to this is, remember that the delta H formation of an elemental state is 0. That's why this doesn't appear in the table, and they don't need to, and it's okay. So we're going to do products minus reactants, each multiplied by the coefficient. So I'm going to take the value of H2O multiplied by 4 plus the value of CO2 multiplied by 3 minus the value of the fuel multiplied by 1. So I get minus 1200 plus 200. So that's negative 2200 kilojoules per mole. On 4, as you could greatly suspect, having ammonium and nitrate in it, if you put this stuff in water, it dissolves great. So we dissolved it, and the temperature of the surroundings went down. So what can we say about the bond energies? Well, it went from solid to aqueous. And the other thing to remember is that aqueous means that the ions are surrounded by water molecules. So the NO3 minus is surrounded, and the water molecules will turn their hydrogen sides to the negative ion here. And that will be repeated, of course, 3-dimensionally all around it. And there will be a bond energy between the ions and the water. So we have the bond energy of the plus and minus ions together, and then them separately surrounded by water molecules. But the energy of the water overall decreased. So energy went into this process, which means that there was more energy contained in the bonds at the end than at the beginning. We know that the bond energies of the dissolved ions to water are greater than the bond between the solid cation and anion to start with. On 5, what we have here is the distance between the nuclei of the bonded atoms, in this case carbon and carbon. And here we have the potential energy of the bond. So if these were at 0.1 nanometer apart, center to center, then you know what they wouldn't be doing is sitting at the lowest potential energy. And that's what nature wants to do, is release energy and achieve the lowest possible potential energy given the circumstances at hand, which is a phrase I've said before, and I would write down if you need to. Nature wants to achieve the lowest potential energy given the current opportunities given to it. So it could be sitting at this potential energy, but that would mean it would have to back off from being at 0.1 nanometer apart. So that's what it'll do. So what can we predict? These atoms will actually separate a little bit more than being 0.1 nanometer apart so that they can achieve the lowest possible potential energy of that bond. For 6, we have 3 so-called half reactions. I know there are 3 of them, so how can they be half? But that's the term I've heard. And together they make up this reaction. So if the delta heats of formation of all these half reactions are X, Y, and Z, what is the overall delta H standard? Well, we're going to add up these values once we figure out how to flip and multiply these half reactions. The easy thing to do is look for chemicals that only belong on one side and are in one place only in here. So I'm going to look for P410. Yep, it's nowhere else, and it's on the wrong side. However, it is still one of these and one of those. So all I got to do is flip this one, and that makes this turn to minus X. On this one, I have H2O, and weirdly enough, that only appears in one place. However, it's on the wrong side and it needs to turn into a 6. So I'm going to flip and multiply this by 6. That's a 6 multiplier. So this turns into negative 6y. The tougher part is this one. The tougher part is this line, I think. The easy part of that one, though, I think, is the P4. Remember, this went over there, and I need to cancel it out because it's not in here, which means I need to multiply this line by 4. So that gives me 4Z. Don't change the sign because we didn't flip it. And then those all add up to be delta H standard. This isn't delta S standard because things have an inherent entropy without the change. They just have it. So this isn't delta. But we're going to take this times the coefficient and subtract out this times the coefficient and that times the coefficient, which is what we've got here. And then we get this value. Evaporation of water clearly is thermodynamically favored in some cases because you see it happening all the time. Though it clearly takes in energy and is endothermic, right? We know that because the hotter you get, the better it works. That's what endothermic reactions do. So how can this be favored if it's endothermic? Well, the answer is at certain temperatures, the transition from liquid to gas creates so much entropy that in the Gibbs free energy equation, the temperature times the delta S value is more negative than that is positive. Because remember, a positive change in entropy is favored. So this will be positive, but then that term turns negative. And I know this is positive. What we need to do is get a temperature high enough that this all turns more negative than that is positive, and we get a negative delta G standard value, which means the reaction is favored at that temperature. Here again, we dissolve ammonium chloride in water, and again, the temperature dropped. So what are we able to say about delta H, delta S, and delta G? Well, here's the reaction. If it's favored and we watched it dissolve, then delta G is a negative. Delta S is clearly a positive because it went from solid to aqueous, plus it split up. So not only is it dissolved and running around, not bonded to its neighbors, but the actual ions split up. So now this is in 2 parts. So for both reasons, the delta S is a positive. The fact that the water temperature went down means the energy was put into this. So the delta H for the reaction is a positive. It's endothermic. On 10, well, I did it my way, which is I like to set it equal to 0 because those inequalities drive me bananas. So I just say, well, the turning point is when delta G is 0 because at one side it's negative, the other side it's positive. So we're going to put in our values. Do not forget to turn this to 0.2 kilojoules. If you leave it at 100 and 200, you will get a very wrong answer. Remember that this is usually reported in joules, whereas that's reported in kilojoules. So I converted this to kilojoules. This goes over. Then we have a negative, negative. So let's just turn everything positive. We divide under, get 500 K is the temperature at which delta G is 0. So what are we looking for? Temperatures where the reaction is thermodynamically favorable. Now, let's examine this for a moment. The delta S value was a negative, which is not thermodynamically favorable. So what I need to do is bring this value down. This one's working against me because since that's a negative and then we subtract, that turns into a positive, and this one is trying to keep the delta G from being in the thermodynamically favored range. So this is the breakover point from this being positive or negative, and I want it to be negative, and I'm trying to keep this number small enough. So what I want is the temperature under 500 Kelvin. I want delta G standard for the whole reaction, and I don't have any delta G information in here, so I can't just do products minus reactions for the delta G data because I don't have any. What I'm going to need to do is use Gibbs free energy. So I have a hole in my information. I don't have delta H and I don't have delta S. So what I'm going to have to do is do products minus reactants for these individually, this column and this column individually. So I'm going to take the product times the coefficient minus the reactant times the coefficient and get the delta H overall for the reaction. Remember that the reason that that's a blank is that elemental states don't have delta H formation values. Same thing for delta S. I'm going to take the products times the number minus the reaction times the number in front and get the delta S. Then I can put both those values in here. Remember to use Kelvin temperature. Remember to turn this to kilojoules. And then we can multiply, subtract, and get delta G standard overall.